Okay, so I'm going to talk about MPI and Fortran. I know most of the people in the HPC community use MPI, at least sort of synonymous in some circles, and of course you all probably use Fortran. That's why you're here. But one of the things that I've noticed is that people who use Fortran and use MPI use old stuff that's bad. And I'm going to tell you why you should change your behavior. I'm also going to give you some reasons why life is not perfect, as life is never perfect, but some things I'm doing to try to fix this, and hopefully make it so that the reasons that you might not like this story in the beginning is not a problem. Okay, so the outline. So what's MPI F08? Why it's awesome, why you should use it. And I'm going to talk about Vapaa, Vita, and some stuff with the ABI. And so for the 2 or 3 of you in the audience who speak Finnish, you'll appreciate some of the words in this talk. But okay, anyways. So MPI has language support for 3 languages, or used to. It has a C API that's used by C programmers, C++ programmers now, because the C++ API for MPI was determined to be useless by most standards, and so we got rid of it under the assumption that it made it easier to get rid of it if we were going to do it right, because you have to delete the old thing before you get a new thing. It's how standards work sometimes. Anyways, we haven't made a new thing because it turns out C++ programmers cannot agree on what the right C++ API is for MPI, so they all build their own, and that's great, fine, they call C. There are 3 different Fortran bindings. They go by the names mperfect.h, the MPI module, and the MPI F08 module. People falsely call them F77, F90, and F08. So mperfect.h is not F77. So if you actually know Fortran, you know that F77 did not have many features, including symbol names longer than 6 characters. MPI init has more than 6 characters. Therefore, this has never been F77, but people will still call it that. Also, we deprecated it because it's bad. You shouldn't use it. You probably are. Almost everyone uses it because it's been around forever, doesn't require modules, it has all sorts of properties in a broken software ecosystem that we all live in, but it's bad. You shouldn't use it. It's not type safe. All sorts of programming errors are uncaught, compilers can't help you, etc. So there's an MPI module which is API equivalent to the mperfect.h header. And that's good that it's in a module. It can have interfaces, and therefore it can do some checking for you and say, by the way, you're just calling this function wrong. The bad news is it doesn't necessarily do that well for a variety of reasons. And then there's MPI F08, which is not actually F08. So we standardized this in MPI 3.0 in 2012. Before Fortran 2015, which became Fortran 2018, existed. At the time, though, there was a dialogue between the MPI Forum and the Fortran standards body to do things in Fortran that would be part of Fortran Next that helped MPI. So we called it F08 because we had to have a name, but really the name should be F18. It's just, if we'd done it then, we would have called it MPI _F15, and you all would be super confused because there's no Fortran 2050. So just accept that MPI F08 means Fortran 2018 support because of the CFI stuff. So there are 2 Fortran modules, and I'm going to tell you why you should use the F08 one. And then I'm also going to indirectly tell you why you shouldn't, but hopefully it won't continue. So the legacy API has all sorts of horrible things because the MPI API, the C API, is really the one that was designed. And the Fortran API is basically the Fortran version of the C API. So in C, we have void star, and buffers are void stars so that you can pass integers and doubles and all these different things to it. Well, that's not actually valid Fortran, right? Fortran doesn't allow, there's no void star, and you're not, if you had an interface, the interface is supposed to be an integer or real. It's not, you can't just pass it anything you want. So it turns out Fortran compilers mostly haven't cared. There's all sorts of code out there that if you actually enforce interface consistency, the compiler gets real mad at you and says, you're passing different versions of a double precision array to DGEM, and it complains about that, and it doesn't really matter, but whatever. So there's all these hacks, pragma ignore TKR, which means type, kind, rank, or just trust the compiler, doesn't care. And okay, so this is bad. This is a bad thing in that you have to go outside of the Fortran standard or rely on compilers to not type check. And relying on compilers to not type check is a bad pattern because compilers are supposed to type check. That's why it's good that we have compilers. Error messages are helpful. So that's bad part number one about the legacy API. The next bad part is handles are integers. Okay, that's because old Fortran didn't have types. You couldn't define an MPI communicator. So everything's an integer, right? So it's a handle, it's an integer that points to an array inside of MPI that holds a communicator. So the bad news is if you mix up the order of your count and your data type or your root and your communicator, compiler doesn't know the difference between a communicator and a count because they're all integers. Okay, so again, you are basically relying on the runtime to segfault or crash and say, by the way, I don't recognize 0x804000 as a valid count. And then you go, oh, that's MPitch's COM world. And of course, none of you actually probably have the hex codes for all the built-in handles memorized like some of us do. So again, it's bad. So we would like type safety. We would like to let the compiler do its job. So the modern API does a lot of good things. The first thing it uses, assumed type, assumed rank. So it's actually the valid equivalent of void star. So now, there's nothing special here, right? This doesn't type check because this allows any type, but at least you're not relying on the compiler to not do its job. You're saying this can be anything. The second, we actually have actual types. So if you pass MPI int or MPI integer or MPI real or whatever to the wrong place, it will say, I do not accept a data type where I wanted an integer, and etc. So this is also good. The other part about this is these object handled types are actually trivially equivalent to the old way, so for interoperability. So if you use some really old Fortran library with MPI, you can just pass it and take %sign MPI val, and it works. So it gives you type safety while also being backwards compatible if you need it to be. The other thing is, and this is fun, right? If you ever want to needle C and C++ MPI users, you can point out that Fortran has this beautiful thing called interface polymorphism. And if we did this thing, and I'm responsible, it made the standard about 200 pages longer, where we made a 64-bit count version of everything, right? If you want to pass more than 2 gigawords, more than 2 billion elements of anything, the C API says, I don't know what you're talking about, you just passed me negative 47 of these things, because integers roll over. But in C, you have to use a separate API call. In Fortran, you don't, because you just have two different interfaces. And if you give it a big number, it uses one interface. You give it a small number, it uses a different interface. We can't do this in C because C11 generic doesn't work the way we want because of weird type promotion rules that don't exist in Fortran. You can't do it in C++ because we don't actually have a C++ API, so we can't define a polymorphic API. Although somebody could build a header that did this trivially, but it doesn't exist. Finally, and I have to switch from bcast to iReceive, and this one is really, really important. When you post a non-blocking receive, you basically say, here's a buffer, and tell the network, stick data in this pointer later, because I'm going to return from a non-blocking receive, and the runtime is going to have this address, and the network, maybe an RDMA network, is going to do an RDMA write into that buffer while you're off computing, as you should be. This is a good pattern. Well, if you don't say that that's asynchronous, Fortran compilers can do naughty things. So nobody actually optimizes reusing arrays as temporary. But what they do is if you have a non-contiguous subarray, many compilers will say, oh, good, I like contiguous arrays because I can vectorize them a lot better. So I'll take your non-contiguous subarray, copy it into a contiguous subslice, and then I'll give that address to the NIC. Well, bad things happen. I'll show you in just a second. So here's what happens, right? So you pass this non-contiguous subarray. Compiler goes, oh, good, temp 500. That's a better thing to give to the library because it's contiguous. The address of temp is given to the network API. And then the function returns and the temp is deallocated. And now the network, when you wait on that operation and tell it to complete, The network goes and writes to temp, which no longer exists. So probably it's seg faults. If not, terrible things happen because it's just writing over memory that, you might have reallocated to do something else with. The network doesn't care. You lied to it, okay? Well, it turns out you need asynchronous. So asynchronous tells the compiler, dude, don't do that, okay? So don't create temporaries. This thing is actually going to be written to out of band at a time later, so you have to keep the address correct. So this is, in my library, the back end that actually does this correctly. So you actually get a CFIC descriptor, which if you are not familiar with this stuff, is the Fortran arrays have something called a dope vector, which was just what we call it. I don't know why we call it a dope vector, but it's an internal representation, and this is the standard C way of capturing that. You give it that, and that thing can then be explained to MPI in terms of its actual native layout. You can, for example, create a non-contiguous data type and then give that to the network, and the network will know what to do with it. And you do forwards and backwards translation. Everything works beautifully. This is actually strictly optional because at the time we standardized this in MPI, we were, some of the people out there were like, well, we don't know when this will be in Fortran, and we don't know when Fortran compilers will support it. And also MPI library implementers are sometimes lazy and don't do everything perfectly right the first time. And so it's optional, so technically you have to check. But if it's a good MPI library, these things are true, and you can do this stuff the right way. Otherwise, you can't, or you can't rely on it working. That's sad, but such is life. So what's the status of things? So if your Fortran compiler supports all of 2018, or at least the CFI, not CFD, sorry, that's a Freudian slip since we're HPC people, supports all of that stuff, and your MPI library supports all the stuff, then you have the privilege of compiling your MPI library every single time, front to back. Takes about, good on a big machine, it'll take, less than 5 minutes. On a Raspberry Pi, it might take 45 minutes. And of course, you're spending about, 14 seconds of the time compiling your Fortran bindings and, 7 minutes or longer compiling all the C code. So this is sort of, some of these things are just build system wonkiness, but the fact that you have to have both the Fortran compiler and the MPI library do everything right for this MPI F08 stuff to work, that's too bad. Okay, so tomorrow, or rather what I have started implementing but not finished, is a solution to this problem. And it was actually motivated by a real problem, which is I work for NVIDIA. I work on the team that is the product group for the Fortran compiler. And it turns out Cray wasn't shipping MPI F08 with our compiler support because our compiler at the time didn't support Fortran 2018 CFI. And even though there was a way to do it, they were just like, whatever, our compiler supports F18, so we'll ship that support and blame you guys for this. So I said, fine, I will fight back, make something that supports our compiler. And in the process, sort of learned a bunch of things and sort of built something that I think is useful, even though our compiler is now working on the CFI stuff. So the other thing is, I'm building this as a third-party library. So you have MPIC libraries on your system, which are largely speaking ABI agnostic, and now you can build the Fortran bindings completely separately. And I've timed it, it takes 1.5 seconds to build all the Fortran support. So you can just include that in your project, and then you don't have to worry about whether the MPI library was built with Gfortran or iFort or NVFortran or CrayFort or whatever it is, okay? We do use optionally one part of the Fortran bindings, which is, well, it's not in the Fortran bindings, it's Fortran support in the C bindings to translate integers to handles. It's dumb, it's optional. That's the only thing I use. Okay, so Vapaa. This is the thing I wrote. It means free as in free range chickens in Finnish. And that means that, MPI F08 is now free range. It can be free to do its Fortran business independent of an MPI library and also sort of decouple Fortran compilers and MPI stuff. So it does all the good stuff that you want it to, in that it sort of works around all the defective implementation stuff. It also does more feature completeness than anybody else, because it turns out the Fortran or the MPI folks didn't think about sort of the direct product of all the things in MPI and all the things in Fortran, and maybe whether that was actually a good idea. So there are some very bad ideas that are not excluded from MPI Fortran support. And I decided, because I'm sort of I'm sort of into, implementing the MPI standard completely, then I would support even the really bad ideas. They don't run fast, but they are at least correct. They won't error out at runtime the way other MPI libraries will. And this also, because I'm separating Fortran and C, it means that the MPI standard ABI, which I'm working on as well, will mean that you'll be able to use Fortran bindings and switch between OpenMPI and MPitch. They won't matter once we have a standard API. So it'll mean you'll do your Fortran business with whatever compiler you want, and then you'll be able to use any MPI and none of this order n squared nonsense that we have today. The defects are due to my incompetence and my lack of code generation usage. I don't have all the features. So what I do is I implement all the features that I want to use, and then any user asks for any features that they want to use, and I implement them. So I have one user right now. It's a CFD guy in Iceland, and he said, "Well, I need MPI IO," so I implemented that for him in 2 days. So if you want to be a user of this stuff and you find the features aren't there, you just tell me on GitHub, complain, and I write them. It's just a little bit of tedium to get it right. There's some optimizations that aren't there yet just because I'm prioritizing other things. And this could be a bug or feature depending on your experience with commercial vendor support, which is the support model is you file bugs on GitHub. You don't have to go through some vendor procurement process and file bugs with the vendor. And this is not an NVIDIA product. So that might be a feature though, because I'm probably more responsive on GitHub than most vendors are with your commercial bug reports. So some things that are interesting. So it turns out if you do a subarray, Cartesian subarray like this, whether it's contiguous in memory or not, and then you ask for not all the elements, like let's say you have a rectangle, and then you say all the elements except the last one. That's non-Cartesian. This isn't actually supported by MPitch because they don't think anybody's ever going to do this. And nobody does, because if somebody ever did it, they'd see the error message and file the bug. However, the MPI standard says that this is legal, so I support it. Whatever, it's not fast, but you are allowed, if you can read it in a book, you should be able to write the code. Standards should be implemented. The other one, and this is really fun. So in Fortran, we have ways to express subarrays. You have a block, and you could take subarrays of it. Fine. And MPI is designed to support that. You can also, in any language, including C, say, here's a pointer that has this many bytes in it. Take a non-contiguous subsection. Nobody that I can recall thought about the fact that MPI doesn't say you can't compose these two things and say, okay, well, I had a 6x8 array, and I'm going to pass a non-contiguous 4x6 subarray as my buffer, while also passing a data type, a user-defined data type that is the 2x4 subarray of the 4x6 subarray. So this is horrible, but it's legal. And again, I'm kind of weird, and I'm like, okay, I'm just going to do this. So I made this work. It's really incredibly nasty. You can do this in 15 dimensions, and you can do this with arbitrary user-defined data types. And it will work. It'll be as fast as you deserve when you do these things, but it will work. And that to me is important. So what do? I have specialized support for 1, 2, and 3D subarrays because, physics, we like 3D. If you want 4D, if you want 60, fine, I could do it. I just don't care right now. I can do generic support for 4D up to 15. That code is really, really special. All this code, by the way, it's 700 lines of code can go from your weird arguments to stuff that the MPI C library understands. And it's fast according to its reasonableness. So the reasonable things are fast and the unreasonable things are slow, but they all work. Except for some weird stuff with some n-dimensional tensors where I don't even know what the right answer is. And so I haven't written a unit test. All right, I'm gonna have to go real fast. Okay, I also detect a bunch of errors, and that's great. Okay, so having told you all this stuff, you should use this, whatever. Now I'm going to talk about auto detection. So you may look at this and you say, look, you have a buffer, you have a count, and you have a data type. Well, this is C-like. Of course, you give all these things, but why? Why do I give the buffer, which contains the count and the data type already, and then I tell it again what the count and the data type are? So you can always mix and match these things, but Why should you have to? If you give a Fortran array, you shouldn't have to tell it twice how many elements are in that array. So I've written a thing, it's just a prototype. Other people have done this, so this is not original stuff. And I don't know if this will ever be in the standard, but this is a way that, if you're always using COM world, why should you have to say that? It should just be the default argument. So Fortran, you can do this. You can do named arguments. You can make everything optional. So I built this thing. If you want to be lazy and you want to have code that is even simpler, where if you want to just bcast and assume rank 0 and assume world, you can do that. And it will infer all the type information, all the count information. It just infers that through Fortran. And including MPI in place and some other stuff. So this really breaks the C-centric design of the Fortran API and actually uses Fortran maybe the way it was intended to be used with MPI. And all the arguments are named, which means you don't have to remember the correct order, right? If you just remember that MPI takes a buff, a send buff, and a receive buff, and a count, and a COM, you can just use them by name. And this, if you're, not literally dyslexic, but if you're API dyslexic and how you remember these things, then you can just remember them by name, and it's going to be great. This project used to be called Galaxy Brain, and then I came up with a Finnish name because I do that for all my stuff now. All right, so just last thing before we go, I'm going to tell you, this has nothing to do with Fortran, except this makes the Fortran ecosystem better in the context of the previous things, which is we're going to standardize an ABI. This is great. The Julia and the Python people love this. This will make Vapaa agnostic to the MPI library again. And you can read this paper, it's open access. So just type this thing into Google and it'll find it. The archive version is out of date, but the ACM version is free. So you just don't have to worry about the paywall. So to summarize, if you use MPI in Fortran, use MPI F08. And if you find your ecosystem is broken, you can try to use Vapaa. You will be completely dependent on me for user support, but that might be better than nothing, better than it not being available at all, or better than it not doing everything correctly. And I'll build something better if you complain loudly. Havaitis shows a way to use MPI better with modern Fortran. If you want, you can sort of take however much of that stuff you want, put it in your thing. And then, the ABI is hopefully coming soon. And then all this order and nonsense of MPitch and OpenMPI and all the CI/CD stuff that everybody complains about will hopefully go away. So that's the end. Thank you. Jeff, is that working? Any questions for Jeff? Yes. Oh, okay.
Hi. This is probably the question nobody wants to hear, but so MPI F08, you say it's designed to work with the 18 standard?
Yes.
How likely do you think you are to be able to use that in HPC usage? Because every time I try to use 2008 onwards, depending on the compiler, especially the NVIDIA compiler, there are things that are missing.
Okay. No. So the first thing is, it doesn't depend on Fortran F18 as a whole. It depends on the CFI API. So the C interoperability part. So CFI _ CDEST ISO Fortran binding.h, just the C interop stuff. Okay. You're absolutely correct. When I started writing this project, NVIDIA Fortran did not support that. And that is why I started the project, so I could work around it, because it turns out we do have dope vectors. We don't document them, but I reverse engineered them, and also I can cheat because I can find the guy who wrote them and say, how does this thing work? I haven't actually did that because since I started writing this project, we have started implementing the CFI stuff. We are not done, but it has been implemented. So if I haven't tested it as much because I'm sort of, I do product-y things in part of my life, and then I do open source stuff, and I don't specialize for our product. And this is one of those cases. But yes, so it's not perfect, but it's definitely not, it's not worse, right? And here's the thing, if none of you use this, none of the vendors will implement it, right? You use this, and then you refuse to use compilers and supercomputers and MPI libraries that don't do things right, and you yell at them, and especially if you're at the right kind of customer that spends a lot of money on computers, you get good support, right? So I'm actually asking you, in spite of the pain that it causes me in my day job, I'm asking you to use this stuff because it's the right thing to do and it makes the world better. And if you all use it, then it gets really high priority with everybody. So
this is music to my ears. I say the exact same thing about all of modern Fortran. Use it and push on the vendors to support it. I wanted to just add one comment there. So in the year 2018, I taught a tutorial that was, the title of the tutorial was Writing Fortran 2018 Today. I really wanted that title because I wanted people to know how much of it they could do then. Even as of 2018, the G-Fortran compiler supported most of 2018. And now today, the Cray compiler, the numerical algorithms group compiler, and the Intel compiler are all fully 2018 compliant. And again, G-Fortran supports most of 2018. And the standards don't get implemented uniformly. Certain features tend to come first. The CINROP features are the ones that pretty much always come first. So even Flang, the newest open source compiler, also supports the CINROP features.
yeah, so for example, we actually were the first ones to implement Fortran 2023, do concurrent locality specifiers with reductions, because we had a strong belief that that was important for GPU programming, right? So we were actually the first by well over a year. There are other things that we are definitely like 15 years behind everyone else because we determined either that they were not practical to implement or they were dumb and no one should use them anyways or whatever, right? So you make decisions like that every day. You know, G-Fortran still doesn't support locality specifiers. So they're not F18 complete.
That's true.
Anyways, but you know, so in my day job, I work on the NVIDIA Fortran compiler, like the product, and I also work on like the Flang side of things too. So we're pushing this stuff really hard. I own the bug ticket for CFI CDESK T, and I have told them how much money is at stake. So, you know, it should be there. And it really is relatively complete. It's just a bunch of people have to use it. There's also some fun things like the standard ambiguity. So everybody thinks that the Fortran standard is like, you know, perfect and everybody understands it. It's all the compilers implement it the exact same way. And that's absolutely not true, right? So there's some stuff in CFI where it'll fail to do the same thing as G-Fortran or iFort, but that's not actually, the standard doesn't say that it has to be that way. It's just that if G-Fortran did it that way, the Intel team was like, customers will complain if we don't match G-Fortran, and now they complain to us if it doesn't match, you know, right? So we get this sort of pseudo-standard behavior based upon who implemented it first. So.
Other questions for Jeff?
Thanks for the interesting talk. I've been on the use MPI F8 train for a long time, so I'm really happy to see that. One reason that I had to roll that change back in a project I was working on was that the PMPI F08 interface was just completely broken in the compiler I was using. I won't name the vendor. There's been a ticket open with them for 5 years about this now. Does Vapaa support PMPI?
So the way I support PMPI and Vapaa is I compile to the C MPI interface. So I am not strictly compliant in the sense that, and I disagree, this should not have been the way the MPI standard did it. They require the PMPI interface to be visible as the Fortran PMPI interface, as if anyone really cares whether you do a send out of Fortran or C, right? My experience, no one cares what language invoked MPI send when you're debugging or profiling. So I support the MPI public interface, and therefore every profiling tool that works with C will trivially work. You will see it as C, not Fortran. And if that bothers you, I may do it, but I definitely get all of, if it supports the function at all, the PMPI stuff should work.
Okay, and we'll set up my slides, and while we're doing that, maybe one last question for Jeff. Anything? Okay.
One
Go ahead.
comment. So one of the nice